Okay, let's talk about how to draw Lewis structures in molecular geometry. So Lewis structure is a 2D structural formula showing the arrangement of electrons around atoms and covalently bonded molecules. For example, the Lewis structure for hydrogen fluoride is shown here. Note that the bonding pair of electrons, the bond, is shown as a line between two atoms, each represented by its element symbol. The non-bonding electrons on the fluorine atom are shown as dots. In most cases, non-bonding electrons are paired, so they're also called lone pairs of electrons or just lone pairs. This example also illustrates the octet rule, which states that atoms form bonds to obtain 8 valence electrons, or an octet. The 2 electrons shared in the covalent bond count towards the octet for both atoms. One exception to the octet rule is hydrogen, which is such a small atom it only contains 1 electron, therefore can only hold 2 electrons, so it can only make 1 bond. For our HF molecule, H has the 2 electrons it needs from the bonded pair it shares with F. F has an octet as well from the 6 non-bonding electrons plus the 2 electrons from the bond. Exceptions to the octet rule. So incomplete octets. We just talked about hydrogen can only hold 2 electrons or 1 bond. Beryllium only has 2 electrons and therefore can only form 2 bonds. 2 bonds yields a total of 4 electrons instead of 8. Boron has 3 electrons and can only form 3 bonds. 3 bonds yields a total of 6 electrons instead of 8. There are also molecules that can have an expanded octet, so many molecules and polyatomic ions have more than 8 valence electrons around the central atom. The central atom can have an extended octet only if it's in period 3 or higher, where there are empty d orbitals available to hold the additional valence electrons. So for example, sulfur can form molecules with an expanded octet because it's in period 3. Oxygen cannot because it's in the second period. Just because something can form an expanded octet doesn't mean that it does, though. So let's talk about how to draw Lewis structures. So the first step you want to do is add the total number of valence electrons for all atoms in the molecule. Remember, the number of valence electrons is equal to the group number from the periodic table for all main group elements. So for example, group 1A has 1 valence electron, 2A has 2, 6A has 6, 7A has 7, so on and so forth. For polyatomic ions, you also need to count the electrons gained or lost due to charge. So for example, for the sulfate ion, we need to add 2 electrons to the total number of valence electrons, since the -2 charge indicates 2 electrons were gained. But ammonium, we need to subtract 1 electron from the total number of valence electrons, since the +1 charge indicates 1 electron was lost. For example, carbon monoxide is CO. It contains 1 carbon and 1 oxygen atom. Carbon has 4 valence electrons and oxygen has 6 from the periodic table. So the total number of valence electrons would be 10 valence electrons. Whereas carbon dioxide, CO2, has 16 valence electrons, 4 from the carbon and then 6 from each oxygen. So let's look at carbon dioxide to demonstrate the following steps. So first, we determine there's 16 valence electrons in carbon dioxide. The second step is to identify the center atom in the molecule. The center atom is usually the atom with the lowest group number, which means that it needs the most electrons to obtain a full octet. Also, the atom with the lowest period number, the total number of electrons will be the central atom. Another way to look at this is that the atom with the lowest electronegativity, i.e. the smallest group and period number, will be the center atom. The center atom is usually written first in the formula. One exception is hydrogen, which is always the surrounding atom. So first thing, write the set element symbol for the center atom. For CO2, carbon is written first in the formula. It has the smallest group number out of the 2 atoms. So carbon is the center atom. Therefore, C is written down. Step 3 is to write the element symbols for all the surrounding atoms for the central atom, around the central atom. Next, we'll draw a straight line, bonds to connect each outer atom to the center atom. You want to subtract the number of electrons in the bonds drawn from the total number of electrons. Recall that each bond has 2 valence electrons, so for each bond drawn, 2 electrons must be subtracted from the total number of valence electrons determined in step 1. Since carbon is the center atom, the 2 oxygen atoms are the surrounding atoms. So we want to take the valence electrons, subtract the number of bonded electrons. So valence electrons is 16. We're going to swap 2 times 2. 2 bonds, 2 electrons each, so we have 12 electrons remaining. Step 4, We want to distribute the remaining valence electrons in pairs, first around the outer atoms, then around the central atom, so each atom has an octet. Make sure to subtract each electron from the total valence electrons to ensure all electrons are used and none are left over. So we determined step 3 that there's 12 electrons remaining, so we'll put 12 electrons around the outer atoms. 12 minus 12 equals 0. The electrons must equal 0. Notice the lone pairs were put on the surrounding atoms first to fill their octets. And then step 5 is to check each atom in the molecule has a full octet, 8 valence electrons. If the atom contains an octet, then the Lewis structure is, if each atom contains an octet, then the Lewis structure is complete. If one or more atoms do not contain the octet, though, we have to move on to step 6. So let's look at this. So carbon has 2, 4 electrons. So 2 from each bond. So it does not have an octet. Let's look at oxygen. Oxygen has 6 non-bonding electrons, 2 bonding electrons, that's 8. 6 non-bonding, 2 bonding, that's 8. So the oxygens are good, but carbon does not have an octet, so we must go on. So if all the atoms do not have an octet, double or triple bonds may be necessary. So first you'll erase all the lone pairs, but leave the single bonds and start fresh with the total number of valence electrons. Add a second bond between the atoms that did not meet the criteria. Add only one second bond at a time. Since carbon did not have an octet, a second bond, a double bond, was added between the carbon and one of the oxygens. Notice only one second bond was added. So you'll subtract the bonded electrons from the total number of valence electrons, which is similar to step 3. So we had 16 valence electrons, minus 3 bonds, 2 electrons each, we have 10 electrons remaining. Once again, we'll distribute the remaining valence electrons in pairs such that each atom has an octet, and then make sure to subtract the lone electrons from the remaining electrons to ensure that all electrons are used. So here we add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lone electrons. We had 10 remaining electrons, we added 10, so 0 electrons left, which is good. Then we'll recheck that each atom in the molecule has an octet. Okay, well let's look. So oxygen here, we have 1, 2, 3, 4 non-bonding electrons and 4 bonding electrons, 2 from each bond. So that oxygen's good. Check this oxygen, 1, 2, 3, 4, 5, 6 non-bonding electrons, 2 bonding electrons. Okay, we're good there. Now let's look at carbon. Carbon has 3 bonds, 2 electrons each, so that's 6 electrons. Still not 8, so we must repeat step 6, adding another second bond. So now we added another double bond between the other oxygen and carbon. Draw the remaining electrons in as lone pairs, and then check the octet. So let's check. Oxygen has 1, 2, 3, 4 non-bonding electrons, 4 electrons from bond, that's 8. Same with this oxygen. And then carbon has 4 bonds, 2 electrons each, so that's 8 valence electrons. So everything has an octet. And then remember, in some cases, the central atom may get more than an octet. Molecules with an expanded octet were discussed under the octet rules section above. For polyatomic ions, square brackets are drawn around the entire Lewis structure. And the polyatomic ion's charge is placed in the upper right-hand corner outside the brackets to indicate the overall charge is spreading among the atoms and the ions. So this example walks you through how to draw the Lewis structure for CH3Cl. So you should go through this yourself and make sure you can do this. Let's look at the nitrite ion though, NO2-. So this is a polyatomic ion. So first we want to calculate the total number of valence electrons for all the atoms in the compound. So valence electrons for nitrogen plus 2 times the valence electrons for oxygen plus the electrons from the charge. So nitrogen has 5 valence electrons, each oxygen has 6, and we have to add 1 electron for the -1 charge. So we get 18 electrons. The next step, the central atom is usually the least electronegative, so nitrogen's the center atom. Then we put the oxygens around it and draw bonds between them. Then we distribute the remaining 14 electrons around the outer atoms first, and then put in the last 2 on the nitrogen atom. See step 3 here. Then we check to see if we have an octet. Oxygen, 1, 2, 3, 4, 5, 6 non-bonding, 2 bonding, so that's good. Same with this oxygen. Let's look at nitrogen, has 2 non-bonding electrons and 4 bonding electrons, so it's only 6. So we need to add another bond between nitrogen and oxygen, which we do here. So we move 2 lone pair electrons from one oxygen and created a bond between that oxygen and nitrogen. So let's check our octets. So this oxygen has 2, 4, 6 non-bonding electrons and 1 pair of bonding electrons, so that's 8. This oxygen has 2, 4 non-bonding electrons, 4 bonding electrons, that's 8. Nitrogen has 2 non-bonding electrons and 2, 4, 6 bonding electrons, that's 8. So we're good. And remember, since this is a polyatomic ion, we have to draw the brackets around the Lewis structure and then put the charge in the upper right-hand corner. Okay, let's talk about VSEPR theory. So Lewis structure shows 2D distribution of atoms and electrons. The molecular geometry or 3D shape of a molecular polyatomic ion can be determined using valence shell electron pair repulsion or VSEPR theory. In which case the basic principle is valence electrons around essential atoms stay as far apart as possible to minimize repulsions. Electron pair repulsion. So the type of electron pair determines how much it repels other electron pairs. Lone pairs repel more than bonded pairs because lone pairs occupy more space than bonded pairs. Therefore, having lone pairs on a central atom will change the shape and the bond angle. So here are the guidelines for applying the VSEPR model. First, you'll draw the Lewis structure. Then you'll count the number of outer atoms and lone pair electrons around the central atom. Then you'll determine the general formula matched up with the molecular geometry, name, and bond angles using the VSEPR molecular geometry table. So that's on the next page. Oh, 2 pages ahead. So here's the molecular geometry table. You don't have to memorize this, you just need to be able to use this so you can have this on your quizzes and tests. But here you have the number of surrounding atoms, here you have the number of lone pairs around the center atom, and that gives you the molecular geometry. So for example, if I have 2 surrounding atoms but no lone pairs, my geometry is linear. If I have 2 surrounding atoms but 1 lone pair of electrons in the central atom, it's bent. If I have 3 surrounding atoms and 1 lone pair, it's trigonal pyramidal. If I have 5 surrounding atoms and no lone pairs, it's trigonal bipyramidal, so on and so forth. So you just need to look at your Lewis structure, figure out how many surrounding atoms you have, how many lone pairs you have on the central atom, and then you can determine the molecular geometry. And again, you don't need to memorize this, just know how to use this table. Okay. Let's talk about polarity of molecules. Electronegativity is the ability of an atom in a chemical bond to attract electrons to itself, or how closely the atom holds shared electrons. So here's the general trend for electronegativity. It increases as we go up the periodic table and over. The one exception is hydrogen's electronegativity is between boron and carbon. So fluorine is the most electronegative element on the periodic table. In general, the closer an element is to fluorine, the more electronegative it is. Again, like I just said, the one exception is hydrogen, which has an electronegativity value between boron and carbon. For example, determine if carbon or chlorine is more electronegative. Note that chlorine is closer to fluorine in the periodic table, so chlorine is more electronegative than carbon. When 2 atoms share electrons in a covalent bond, they normally don't equally share the electrons if one atom is more electronegative than the other. This tug of war for electrons shared results in the atom with a higher electronegativity, pulling the electrons more strongly towards itself, thus forming a partially negative, electron-rich end of the bond. Such electrons spend less time around the other atom. That atom becomes partially positive, electron deficient. Thus, one atom is partially negative and the other is partially positive. So the bond has 2 poles, and this is called a dipole. And bonds with a dipole are polar covalent bonds. So if we look here, hydrogen and fluorine. Fluorine is more electronegative than hydrogen, so it's partially negative. Hydrogen is partially positive. That's what these delta notations are. So we put this delta minus by the more electronegative atom and the delta plus around the less electronegative atom. Dipoles are also indicated using an arrow with a cross. The cross shows the positive end, and the arrow points from positive end towards the negative end. So this shows you this side's positive and this side's negative. In general, the greater the difference in electronegativities, the more polar the bond. In some molecules, two atoms have equal or very close electronegativities, so they share the bonding electrons equally in what is sometimes called a nonpolar covalent bond. So for example, the hydrogens in an HH bond and H2 are shared equally by the hydrogen atoms, so this is a nonpolar covalent bond. To determine whether an entire molecule is polar or nonpolar, we're going to refer to the following. So for diatomic molecules, so molecules consisting only two atoms, when the two atoms have equal electronegativity values, there's no dipole, so the molecule is nonpolar. If the two atoms have different electronegativity values, there is a dipole, so the molecule is polar. For molecules of 3 or more atoms, we want to just follow this chart. So first you want to draw the Lewis structure before you try to determine polarity. The first question you ask yourself is, are there any polar bonds? If the answer is no, then the molecule is nonpolar. If the answer is yes, then we need to answer the following questions. Are there lone pairs on the center atom? If the answer is yes, then the molecule is polar. Are there different types of surrounding atoms? If the answer is yes, then the molecule is polar. If the answer is no to both, so there are no lone pairs on the central atom and there are not different types of surrounding atoms, then the molecule is nonpolar. So let's look at CHCl3. Is this molecule polar or nonpolar? Well, first, are there any polar bonds? Well, carbon and hydrogen, their electronegativity is really close, so it's considered to be nonpolar. But the difference between carbon and chlorine is quite a bit. So carbon and chlorine, that's a polar bond. So for the first question, our answer is yes. Then we'll ask, are there any lone pairs on the central atom for CH3Cl? No. So that's the answer to that question is no. Are there different types of surrounding atoms? Well, yes. We have hydrogens and we have chlorine. So the molecule is polar. We draw it like this because carbon is more electropositive than chlorine. So we talked about this molecular geometry table. Just to note here, these wedges and dashes, they're bonds. This is just showing that if it's a wedge like this, it's coming out towards you. If it's dashes like this, it's going away from you in 3D. And these are lone pairs. This is not a bond, though. There's no bond from an atom to a lone pair. This is just showing you where the lone pairs are in space. So I asked you to do this nomenclature practice last week, and I posted the key for this. But then down here, go down. Here is practice with drawing Lewis structures, determining shape, and determining if molecule is polar or nonpolar. So you should do these, definitely. And you should definitely practice this more than just beyond what's on here. There's a lot of practice problems in your book, and I just really recommend you do that because this is something that's not too terribly difficult, but it does take quite a bit of practice to become confident. And so you definitely should be practicing this. It will be on tests and quizzes. And you can really just choose any molecule and start going. Draw the Lewis structure, figure out the shape from the table, and then determine if it's polar or nonpolar. And again, this is on D2L. So that's all I have for molecular geometry and Lewis structures.